So good morning to all of you, my dear students. Welcome to yet another session, early morning session of CCNA-1, Introduction to Networks. Okay. So we are 25 students in, counting. So let's start today's session. So we are here gathered doing our CCNA lab. Okay. So the CCNA that we're doing is Cisco Certified Network Associate, consisting of 3 levels. The first level is called Introduction to Networks. The second level is Switching, Routing, and Wireless Essentials. The third level, the final level, is Enterprise Networking, Security, and Automation. Okay, these are the 3 levels to get your CCNA certificates. Okay, so we are here gathered doing level 1, Introduction to Networks. Okay. At the end of Introduction to Networks, you do an exam, which is an online exam, as well as a skill-based exam. If you have done these 2 successfully, you should get your CCNA certification. Okay. CCNA-1 certificate. Okay. So welcome to our CCNA-1, which is Introduction to Networks 7.0. Now, there are some of you who are perhaps new and are joining us today. So these students, please switch off your microphone. Thank you. Yes. Lord, you are new. Yes, these lecture slides, I'm recording these sessions, and then you can find it, the links on Moodle. Okay. There are some of you who are new and you don't have a NetAcad identity yet. No worries. After the session, I will be creating NetAcad identities for you after going through these slides. For now, just pay attention to the slides. Okay. So we have already gone through the first 2 chapters of our CCNA-1 Introduction to Networks. Today we'll be doing Module 3, Protocols and Models. As we go through this, you will realize that some of the things we study here are overlapping the things that you study in the lecture, the concepts that you study in the lecture and in the tutorial are heavily overlapped over here. We'll be again studying these. But what you study in the lecture and tutorial, they are based mainly on the theoretical aspects. But here, we do the actual activity in the lab. Okay? How we configure our internetworking devices, our intermediary devices, especially switch and routers. Okay, what is the internetworking operating systems commands? How do you configure your different devices? So these technical aspects of networking is what you are going to learn. These skills you will develop. Okay, so what you study in the lecture and tutorial will complement what you study here in the lab and vice versa. Lo, your question says, no, you don't need the PowerPoints. You know why? Because once I create for you an identity on NetAcad, you have the whole, whatever PowerPoints I'm presenting over here, those PowerPoints, actually the whole structure and of the course is in your NetAcad. You can actually go and you can click on it, and the NetAcad course, instead of the PowerPoints, it delves much more in depth into the course. And that also has got chapter 1 until chapter 17. Exactly the same thing. Okay. Yeah. Once you are inside NetAcad, you will see it has got a system whereby it will ask you to go through each chapter. And it is a multimedia session, it's like showing you pictures, and it's much more interesting than this. You can, of course, again, go through these lecture slides by going through the video if you want, okay? Or you can do a self-paced learning. That's the whole point of NetAcad. You can go through the course, page by page, which is very in-depth, much more in-depth than what we have over here, okay? Now let's start with Module 3, Protocols and Models. So today we'll be learning the concept of following a common rule, okay? We will learn about why do we need protocols? Why is it necessary? What are the protocol suites, okay? And why do we have to follow, adhere to a standard protocols and follow some standard organizations? Why do we have to follow that? What are the different reference models that we have? Why do we have to follow the TCP/IP model or the OSI model? Why? Why do we have data encapsulation? How data encapsulation allows your data to be transported, okay? And how data access happens. How your local hosts can access data on a network. So we'll be actually learning some things that perhaps will put networks in perspective. So let's start. The first concept is having a rule when you are communicating. If you think about communication, generally, we have got different kinds of network. That is true. But when you want to network, you have to ask the question, how this communication is possible? Obviously, there should be a sender, there should be a receiver, and in between, there should be a channel that takes the that takes the message through that channel from the sender to the receiver. Okay, so these are the three important components that you need. And that is why we need certain rules for communication. And these rules are actually protocols that we follow. Okay, when you send your message, it has to be converted into a specific signal which can travel through the transmission medium. Transmission medium are of different kinds. That is what we're going to learn in chapter 4. Okay, we have got copper wires, we have got even wireless medium. So these are some of the ways we can actually transfer our message. So once the signal is received by the destination, okay, then our goal is complete. Now, it's very important for the message to be sent in a way, okay, that can be read. Example, just look at the two outputs over here. Obviously, the second one is much better formatted and can be understood better than the first one. The same goes for a message, okay? That is why you should have a rule so that nothing is lost. The message is sent properly. So protocols must account for an identified sender, a common language, speed and timing of delivery. And how do you know that the message has been delivered? Okay. When you study at your lecture, you will study an issue which is called two-army rule. Okay. Now, how do you ensure that once you send the message, the receiver has received your message? Okay. So all these things has to be taken care of. Okay. So in order to make sure, the requirements to make sure that the message has been successfully sent, there are 5 important things we'll look at. First is message encoding. How do you format and encapsulate your message? What is the size of your message? What is the timing of your message? And what are the delivery options? Now, let's delve into these 5 concepts in more detail. Okay. First, you have to encode your message in a form that can be able to be transferred through the medium. Okay. So we know that the message is transferred in the medium through a special bits. Okay. Through binary bits machine language. Now, in order to take that English of your data, English text of your data, or the voice that you're transmitting, or the video that you are transmitting, um, you have to transmit it in a form which is converted into binary format. So it has to be properly converted into that binary format. So you should have a encoder, okay, that does this for you. And at the receiving end, you should have a decoder that again assembles your message and sends it and gives it to the destination in the way that you want, that you send it. Okay. So this is the first requirement, encoding. Second, you need your message formatting and encapsulation to be done. Okay. It has to follow a certain structure. That means when you're sending your message, it has to be in a special structure. In that structure, the message should know where is it coming from? Where is it going to? That means what is the address of the place I'm coming from? What is the address of the place I'm going to? All those information should be inside your message. That is destination IP address, source IP address. All that information should be part of the message. Okay? So that when it comes to the destination knows where it has come from and whether this destination is the correct address. Okay? Along with other flags. Okay? Like payload length, next header. Okay? You study this more in detail in the lecture. Okay? What are the different components of your message, how it's formatted and encapsulated. The third thing that you need to know is what is the size of my message? If I'm sending my voice through the network, it's not going to actually carry my voice. It has to be converted into smaller chunks, okay, in a format that can be transferred through the medium, okay? So how do we convert it into bits? Okay, we take the data. How do we segment it from? How do we take the data and segment it? And then how do we take the segmentation and convert it into packets? And then how do we take the packets and further change it into chunks of data, bits? So all these you have to take care of, okay? The proper size so that it can be transferred. Okay. And when you send your message, you should know that it should have a certain timing. Timing consists of 3 main parts: flow control, what is the rate of data transmission, response time. When you send your message, you should know that the message receives the destination. How long you have to wait until you know that the message has reached the destination. Why this response time is important? Because if you don't get an acknowledgement from the destination, then you have to send the message again. That means your message has not reached the destination. That is why a response timeout is important. Okay. And of course, access method, which determines when you can send the message. You cannot just send the message in heavy traffic. Otherwise, your message will be lost. Okay. in order to avoid collisions, you have to make sure that there is a proper access method. Okay. And finally, the fifth concept being the message delivery options. Now, usually there are three kinds. One is unicast, when you are sending a message from source to another single entity, another single device in the network. It can be multicast, where from one source you are sending to multiple destinations, can be more than one. And the final one is broadcast, where you're sending from one source to all the devices in the network. Now, when we say the word broadcast, it is specific to IP version 4 addresses. Okay. IP version 4 addresses, my dear students, was the initial way of addressing system that we had. Now, unfortunately, a few years ago, we realized that IP version 4 addresses are not enough, especially public internet addresses, because we have got so many devices, millions and millions of devices. So they came up with a new IP version, IP addressing system known as IP version 6. Okay. So in IP version 6, there's no such thing as broadcast. They only are used in IP version 4. In IP version 6, we have got something called Anycast, which we'll be studying more about in this CCNA1. Now, you as professionals, as network professionals, network engineers, you have to know both the numbering system. Okay, you have to know IP version 6 because you're going to learn this new numbering system. And you cannot give an excuse that, okay, I will just stick to IP version 6. No, you cannot do that, because for the internal network, people will still use IP version 4. Okay? Public, yes, IP version 6, but most of the networks are going to be your Ethernet local area network. So you still have to configure it using IP version 4. So no excuses for all of you. You have to learn both. As we go along, my dear students, if you have any questions, you can ask me or you can type it out. Okay, I've got another computer here, which I can see your questions. IP version 4 is a 32-bit addressing system. Okay, and IP version 6 is 128-bit addressing system. Okay, 32 bits consisting of 4 octets. Okay, so each octet is 8 bits. So 8 times 4 is 32-bit addressing system. Okay, we'll be going through this over and over again, because an important part of Introduction to Networks CCNA1 is getting your addressing system understood and implemented very well. Okay, that is the basic need. And in fact, if I can tell what is the most challenging aspect of CCNA1, okay, if you ask me CCNA1, CCNA2, and CCNA3, the most challenging of these three is CCNA2. CCNA1 is like a breeze. But if you again ask me CCNA1, which is the most challenging part, that would be the IP version 4 addressing system. Once you get that, that is chapter 11, topic 11. Once you get that understood, then everything is a breeze. Everything is easy. And think about it. The first thing you have to do in a network is configure the IP addresses. If you don't do that properly, then, if in your skill-based exam, if you follow the wrong IP address, that's it, fail. No communication. So that is why knowing the IP address is very important. And I keep, telling you all about it over and over again. Okay. So unicast, sending from a sender to a single receiver. Multicast, from one sender to multiple receiver. And broadcast, from the sender to every device on the network. That is the local area network. Okay. So let's continue with the concept of protocols. What are the rules that we have to follow for communication? So these devices that the protocols should be implemented in can be your hardware, your software, okay? And every protocol has got their own function, formats, and rules, okay? You have got a network communications protocol, a network security protocol, you got a routing protocol, you got a service discovery protocol so that you can detect devices in the network and so on, okay? So in order for the communication to happen, the devices should follow a certain standard, okay? And these protocols have got a set of functions. How do they do addressing? How do you make sure that the data is reliably delivered from the sender to the receiver? How do you do flow control? How do you do sequencing? How do you do error detection? If there is an error, how do you retransmit it? What application do you use to do the communication? When you look at all these functions, you have to ask yourself, which protocol do I create? And if I just create a protocol, I should have layers of this protocol, and each function has to be taken care of at a certain layer. Okay, for example, I told you data has to be converted into chunks of segments. Which layer takes care of that? Which layer of my protocol takes care of that? Then the segment has to be converted into packets. Which layer should take care of that? The packet has to be converted into frames. Which layer should take care of that? And finally, the frame is converted into electronic codes of bits, that is zeros and one. Which layer should take care of that? You see, those details you have to know, okay? So the network requires several protocols, okay? And some examples of these are your hypertext transfer protocol, which governs the transmission of data from a web server to your web client. That's what you always use when you're on the internet, okay? Even in a distributed system that we are using like WebEx over here, there are certain aspects of HTTP used, okay? Transmission control protocol, which manages flow control and guaranteed delivery and manages individual conversations, okay? Internet protocol, both TCP and your IP, both of them ensure that your data is transferred without fail from the sender to the receiver. The Ethernet protocol, which allows uh, data to transfer from one NIC to another NIC. Now, these are some examples of protocols that we have. And these protocols, again, you have to ask yourself, which layer should take care of which protocol? Which set of rules it has to follow? Look at the last one, Ethernet. Delivers message from one NIC to another NIC on the same Ethernet local area network. Okay? A local area network is within an organization. Okay? An IEEE form of a local area network, a specific local area network, is called Ethernet. Okay? So when you talk about a local area network, that means that local area network will have one network IP address. Okay? Be it IP version 6 or IP version 4. Okay? So that means it will have the same network address. Now, your question should be, what is the same network address? Okay. Now, look at the device I have over here. What I do is, I think, yeah. Look at this device I have over here. Okay. This notebook. Now imagine it has an IP address 192.168.1.1. Okay. Now we are trying to find out what is the network address of this network. Okay. Here you see, this is the network over here, and this is the internet, and this is perhaps another network. Okay. Now I have already told you since the first session that if you want to communicate uh, in a network, you need intermediary devices. What are the intermediary devices that we're here to study? Switches and routers. Okay. So in the same network, the communication happens between a switch. Okay. So in an Ethernet, all the devices will have the same network address. But the moment you go out of the network, then you need another device, which is the router, which connects two different network addresses. So when we say different networks, we're talking about different network addresses. So coming back to my original question, what is the network address of this network over here? Okay, what is the network address? So the question should be answered with something known as a subnet mask. Okay, just not the IP address, you should also have a subnet mask. For example, if I say my subnet mask for this network, there, the IP address of this device is 192.168.1.1. That's very good. Now you have to ask yourself, in this address, which one is the network portion of the address and which one is the host portion of the address? So every IP address, version 4 or version 6, has got two divisions. A network portion of the address, which is the same for every device in the network, and the host portion, which is unique and different. Okay? So you have to ask yourself, for this IP address, version 4 IP address, which one is the network portion and which one is the host portion? See, there are 4 octets. Out of these 4, which one belongs to the network and which one belongs to the host? Answer is, what is the subnet mask? So the subnet mask is given to you as 255.255.255.0. So when you translate this subnet mask from decimal to binary, it will look something like this. So that means the network portion is all the ones. That is 8 plus 8 plus 8. That is 24 bits are for network portion and 8 bits are for host portion. What does that mean? That means 192.168.1, you see, these 3 is the network portion. Host portion is only this. So in this network, these 3 octets will always be the same number. And this one will keep on changing for every device. So going back to my original question, what is the network address for this network? The answer is, you have to just take the first 3 octets because the subnet mask says this one is the network portion, the ones. So what is the network address of this network? The network address of this network is 192.168.1.0. Get it? That is how we know what is the devices in the same network address and what is the devices in a different network address. Okay, so a small quiz. Now let's go to this network. Okay, so let's say for this server, I have got a network device which is 192.168.3.1 and my subnet mask is 255.255.255.0. So the question is, for this network, okay, for this network, what is the network address? Anyone? You can type it out. Yes, Cassandra, you're right. Okay, that's 192.168.3.0. Okay, now you have to be careful. Sometimes if it is 255.255.0.0, then that means the network portion is no more 24, is now 16. The host portion is going to be 16 as well. 16 portion for host, that means you can add more devices in that network. Sometimes you have got 255 only for network, and you have got 24 bits for the host. Now do that calculation, how many devices you can add then. Okay, so we'll be studying these over and over again, and I'll be quizzing you and repeating this over and over again until you are really good. It becomes second nature to you. Because IP version 4 addressing is something tricky, and you have to get used to it. There's no way around it, my dear students, in this unit. If you want to get your skill-based exam pass and successful, you have to understand this concept. And I'll be keeping on repeating until you get tired of it. Okay, now let's move on. So let's go to some protocol suites. Okay. So we had Cassandra, we had John Paul. Yeah, correct. Yes, for the second case, it will be 192.168.0.0. Yes, very good. Okay, let's move on to the concept of protocol suites. So there is a way to communicate by following a set of protocols, okay? Protocol suites that communicate with each other. They follow a set of international rules, okay? And these protocol suites, you know, they have got different layers where, like I told you, the data chunks are converted from one form to another in different layers. Okay, from higher layer to lower layer. Okay, higher layer. If you look at your OSI model application layer, down to the lower layer, like the physical layer. Now, this is something I told you. Whatever we study here is going to overlap what you study in the lecture. Okay. So, two main protocol suites that we are interested in. Okay. That could be our Internet Protocol Suite, or TCP/IP, where we have got application layer, transport layer, internet layer, and network access. Right at the physical bottom is your network access layer. Then is the internet, then is the transport, and then is the application. Besides that, we have got another standard, which is from OSI. Okay. Now, this is developed by ISO, and it has got 7 layers. Okay. That one also can be used in different layering. And we can see, I'm going to show you how the TCP/IP layer maps into the OSI model. We also have companies coming out with their own proprietary suits. We have got Apple Talk for Apple devices. We have got Novel Network and so on. Okay. So amongst these protocols, what we'll be paying attention to is the TCP/IP protocol suite and the OSI model, the 7 layers. Okay. So if you look at your TCP/IP, at every layer, something happens. Okay. So network access, the protocol stack that it has takes care of your Ethernet. In the internet layer, your internet protocol. In a transport layer, your TCP. In your application layer is where your HTTP protocol works and so on. Okay. Perhaps this one gives you a better indication of which protocol suite works at which layer as far as your TCP/IP is concerned. This is much more detailed, okay? For your TCP/IP, okay, it's a standard protocol suite which is freely available to the public, okay, and can be used by any vendor manufacturer, any vendor, okay? It's not vendor specific. It is something which is endorsed by the networking industry and approved by your standards organization. And right over here, look, for example, in your transport layer, we have got a connection-oriented protocol working here, which is your TCP, and connectionless, which is UDP. Details about this you're going to study in your lecture. Application layer. So many protocols working. Domain naming system, domain naming system, so that you don't have to type IP addresses. Rather, you just type www.bbc.com. DHCP, rather than giving IP address to the thousands of devices I have got on my network, I make my router automatically give IP address to every device that joins the network. Okay, email, SMTP, POP3, IMAP. Okay, ensuring that when I send an email, it goes to the server. And if I get a new email, it comes from the server to my machine. File transfer, video and web services, all of these protocol suites work on the application layer. Now you get an understanding, why do we need layering? So if you are sending your data from a web server to your web client, okay, a TCP/IP communication process that is happening. So what happens is the web server will actually send the data in the form of bits, which is zeros and ones, machine code. Okay. And once it is received, once it comes to your client machine where you're sitting at, this will be converted into Ethernet frame. Okay. Now, there is a specific layer that takes care of it. And that one is your, if you look at your OSI model, it is your layer number 2. Layer number 1 is physical layer. Layer number 2 is your data link layer, where these bits are converted into frames. Then you go to layer 3, network layer, where it is converted into packets. Then you go to layer 4, transport layer, where segmentation happens. And then you go to the top 3 layers, which we are, we can just call it application layer now, where you get your user data. So this encapsulation and de-encapsulation happens every time a web client talks to a server, and every time a web server sends the data to the web client. Okay, every time you download a page on the internet, this is what happens. So looking at some of the standards organization that we have seen TCP/IP. We have got ISO's 7-layer model. Now these layers actually are, and other solutions are suggested by these organizations. You can see some of them over here. They ensure that there is interoperability, there is competition, innovations, okay? And all these are non-profit organizations, okay? They're not out there to earn money from us, but to make sure that there is no chaos. So tomorrow, if I'm going into business of manufacturing a device, an electronic device, I cannot just do my own thing. I have to be following a standard, communicate with these bodies and follow a standard. Now we are going to see who are these bodies, okay? We have got the Internet Society. We have got the Internet Architecture Board, Internet Engineering Task Force, okay? And the tasks that they do. We have got the Internet Research Task Force, okay? So these these standards, they're not controlling the internet. The internet, there's no one person controlling it. But we have got these bodies who, try to bring some order into the chaos. It's a very dangerous word to use, to say that somebody is actually controlling the internet. Nobody likes that, okay? Nobody. So that is why we have to stress that and say that these bodies, they are not actually controlling, but rather making sure that everything that we create is will be part of the system. Okay, nobody is doing their own thing. Okay, in the early days of the computing, even IBM standard computers, your PCs, couldn't the data inside could not be transferred to another one. IBM PCs that could only communicate with IBM PCs. Okay, if you had the HP PC, you couldn't communicate with that. So, you know, once you had an international standard and everybody adhered to that standard, then communication was much more easier. We also have the Internet Corporation for Assigned Names and Numbers. Okay, no, this is what kind of domain naming system that you're going to use. So Internet Assigned Numbers Authority, which tells you your IP addresses, and why do we need IP version 6 and can't why IP version 4 is not good enough. So they come out with all these solutions. Okay, we have got our IEEE, we have got our EIA, Electronic Industries Alliance, we have got the Telecommunications Industry Association, International Telecommunications Union, Telecommunications Standard Sector. So these are so many institutions, okay, so many acronyms, but they are all there serving a purpose to make sure that there is a standard and everybody follows it. So let's look at the two main reference models that we have. And these two reference models are our OSI model and the TCP/IP model. Okay. In our OSI model, we have got these 7 layers starting from physical all the way to application. Actually, initial days, there was a division, but now application in OSI model encompasses presentation and session. Okay. In your TCP/IP model, as you know, there are only 4 layers: network, internet, transport, and application. And these are the protocols that work in these suites. Okay. So over here, TCP and UDP, you see, for both of them is transport. So you can see how the OSI model maps into the TCP/IP model. Okay. The first and the second layer of the OSI model, that is physical and data link layer, map into the network access model. Okay. And these are the protocols: Ethernet, WLAN, SONET, SDH. Okay. SONET and SDH is mainly your fiber optic communications. Okay. So when you look at these, you can see that how they map to each other and which specific protocol is taken care at which layer. Okay. Again, look at before we continue, again, I would like to say, look at this network. This is one Ethernet, one LAN. Okay. If you look over here, what does that mean? One LAN. You see, what is the communication device they use? This is a square device. It's a switch. It's a representation for a switch. So what does that mean? That means all of them are in the same network. What is the meaning of same network? That means all of them have the same network address. The same goes for this. One Ethernet. That means all of them are in the same network. What is the meaning of same network? That means all of them have the same network address. Get it? Now, when you connect this network to this network, two different network addresses, then you need a special intermediary device known as a router. That's what a router does. Connects two different networks together. What is the meaning of different network? That means two networks following different network addresses. Now let's delve into this more so you can understand it better. First, why do we have a layered model, TCP/IP or OSI? Why? Okay. First of all, they assist in protocol design and which protocol takes care of a different layer. They foster competition. They prevent technology or capability changes in one layer from affecting other layers, okay, up or below. And they provide a common language, okay, to describe networking functions. So the OSI model, you can see right from the physical layer to the application layer, which layer takes care of what, okay? So the physical layer describes the means to activate, maintain, and deactivate the connections. It's actually the place where actually the data comes in bits, okay? Machine language bits. Data link layer takes care of exchanging data to the top or to the physical bottom by converting to data frames, okay? As I told you, and this is something you'll be studying in your lecture as well over and over again. Network layer, what you do to the network layer, how do you convert these frames into packets, and how do you convert the packets into frames? Transport layer, how do you take these packets, convert it into segment, or how do you take the segment, convert it into packets? And then when you transport the data in the transport layer to the sessions, presentation, and application, how do you actually convert it into data that the user can see and understand? Another important thing you have to see over here, in the data link layer, what we take care of is the actual MAC address of your NIC, Network Interface Card, okay? So your MAC address, which is a unique address of that network device. If you have a network device, be it an IoT device, be it a computer, or be it even a simple, humble camera, which has got a network identity. Any electronic, that's why I use the word IoT, which has got a network identity. It should have a MAC address. So that MAC address is taken care of in the data link layer. Now, when you go to the upper layer, network layer, here we have got the IP address layer. So the network layer will take care of your IP addresses. Okay. Now you have to ask a question. Why do I need IP addresses? Why can't I just be satisfied with my MAC address in the data link layer? The answer is very simple. Because the MAC address, communication can happen within a Ethernet, within a LAN. But the moment you go out, okay, you need something more complex. When you go out of your network, you need a logical addressing in the form of your IP addresses, in the form of version 4 or version 6. We'll be looking at that. Here is your TCP/IP model consisting of network access, an internet, a transport, and application. And how they map into each other again. Okay. So let's look at data encapsulation now. So in your transport layer, what we do is segmentation. Convert your data into chunks of smaller units called segments. Okay. Why do we segment? Two important reasons. It increases the speed of the data transfer, and it gives efficiency. If the segment that you have sent is not sent, it will be retransmitted. Okay. Uh, if you are sending data, you have to retransmit. For example, if you're sending a video, you have to retransmit the entire video. But if you have got segments of it, then the segment that is missing, only that segment you will transmit. Okay, that's the whole idea of taking a big chunk and dividing into smaller chunks. Another thing is when you have these segments, each segment has got a number associated with it. Okay. So that at the receiving end, these segments again will be joined together and be presented as your data, which you can read in the application layer. So that's what is important as well, sequencing the segments. Now, when you send data right from your application layer down to your physical layer, okay, these data, let's call it protocol data units, okay? These data right from the application layer where it is data and it comes down to your transport layer. This data is subdivided into sequences of segments. These segments, when they come to the network layer, they are subdivided into packets. And when they come to the data link layer, they are subdivided into frames. And in the physical layer, into bits. Okay. Once they reach their destination, the other thing happens. Okay. So the received bits come to the physical layer and then they are converted into frames. Where? In your layer 2, data link layer. In the network layer, converted into packets. In the transport layer, converted into segments. And then go to the top layer, application layer, where you can see it in data format. Okay. Now we go to data access. Like I said, if you look at your OSI model, where you have got physical layer going up to the data link layer, going up to the network layer, there is something that you have to know about these three networks. First of all, the physical will take care of the timing and synchronization. The data link always takes care of the MAC address, your hardware address of the network. The moment you go to the network layer, that is where we look at the IP addresses. Okay. Transport layer will look at the ports, and the upper layers, mainly the application, will look at the apps. Okay. So whenever you're in the data link layer, it will be asking, what is the MAC address? Okay, the machine address. And the machine address, you will study in your lecture as well, is a unique address which is hard-coded on your NIC. Here, this is your NIC. And this is unique. How do you ensure that it is unique? Very simple. Every manufacturer will go to a special body and they will say, I want to, for example, Samsung says that I want to manufacture this month 1 million TVs. okay, and I need 1 million MAC addresses. So they go to this special body, which is a standards organization, okay, and they say, what can I use? So they'll say, okay, the first part of your machine code is going to be something related to your Samsung identity, and then you can use from this number to this number, okay? So this will ensure that the MAC address that they are using on their machine is unique all around the world. Okay, it is not repeated. Now, the problem is you cannot just use the MAC address to communicate outside the network. So when you go outside the network, when you have the source and destination, you need to have an IP address. Okay, now let's delve into this in more detail. Okay, so the packets that you're sending, okay, when you're sending from your PC1 uh, to the destination, it has got the source and the destination IP address. Now, over here, for example, um, if I ask you what is the network address of this network, so this, you see, a router means this is one network, okay? Why did I include? Because this section of the router is also part of the same network. That means this section right over here, where the connection happens to the router, this one also will be in the same network. So the question is, what is the network address? Your answer should be, I don't know. What you need to know? Give me the subnet mask. Okay. So let's say I give you the subnet mask, then only, okay, I thought that, okay, maybe another slide. When I give you the subnet mask, then only you can say, what is the network address? So for now, whenever you are sending your data from the sender to the destination, remember, the packet will have, when we say layer T, that means the network layer. It will have the source IP address, where is it coming from, and the destination IP address, where is it going to. So you can see from the network IP address version 4, you can see right over here, can you see the difference? So definitely they are on different networks. You see, this is 172.16.1.99, class B, and this is class C. Okay, don't worry about the different classes. We'll study that later. Yes. So if you look at this address that I have over here, uh, you have got the network portion of the address and the host portion. Okay. So the question is, how do you know the network portion and the host portion? By looking at the subnet mask. So if this is my subnet mask, what is the network address of this network? Anyone? Yes, very good, Cassandra. It's 192.168.1.0. So every device in this network, you can only change this section. So another question is, how many devices you can add to this network? That is 192.168.1.1 until? Anyone? Give me a number. 10 devices, only John Paul. No, not 10 devices. You can add more than that. Yes, Cassandra, very good. 254 devices. Okay. Yes, this is your network address. How many devices you can add? Okay. 192.168.1.1 all the way to 192.168.1.254. So you can see the network address is always the same. What is changed is the host portion from 1 to 254. Okay. I'll be repeating this over and over, my dear students, until it sinks in. I have another question. Why can't we use 255? Anyone? You can Google and find out. Anyone wants to try? Why can't we use 192.168.1.255? Daryl, we don't start from zero. Zero is the network address. You cannot use this to give an IP address to any device. Okay? That's why we say network address. The first IP address that you give is this. The last one is this. You can never give this address. Actually, you can never give this address because this address is reserved. Yes, Cassandra, well done. It is reserved for broadcast. Remember, we have got in IP version 4, we have got a broadcast address whereby the sender can broadcast to every device on the network. This is the broadcast address, 192.168.1.255 for that network. Okay? So, the broadcast address is always the last address which you cannot give to any device. Okay? We'll be studying about this more in subsequent chapters. Now, so when you're sending your data, okay, look, when you're sending it from your local network, this is your local network over here. When you're sending it from your local network to another network, since this is one network address and this is another network address, now that you know what is the meaning of network address, you have to use the intermediary device in the form of a router. So in this network, once you have your subnet mask, you can know that my network is 3 portions. So the network address is 3 octets. So the network address will always be the same. What will be changing is your host portion. Okay? And you have got an option to give from 1 until 254. When you're sending data within your network, okay, within a network, every device will have a unique NIC. That is a unique MAC address, okay? So you will be sending your source MAC address and your destination MAC address. And it can find it in the network very fast, okay? But when you're sending outside, then perhaps you need more information in the form of your logical address. That is your layer 3 addresses. Layer 3 as in the network layer. Your physical addresses work in the data link layer. Okay? So when you send it outside, okay, when you're trying to send your data from, let's say, this IP address, this MAC address, to this IP address and this MAC address, okay, how does data travel? So you can see the network address of this network is 192.168.1.0, okay? What is the network address of this? That would be 172.16.1.0, example, okay? So how do we transfer data? If you can see how the data is sent, okay? The issue is, within the network, what you have to do, your layer 2, okay, which is your data link layer, which is taking care of the MAC address, okay, will look for the default gateway. Now the question is, what is the default gateway? This right here is your default gateway. You see this connection to the router? This will have an IP address which is the same as the network. Usually, the default gateway has got a IP address 192.168.1.1. The first, the first IP address, which is .1, usually we give it to the router. Okay. And then we distribute the other addresses accordingly. Okay. So this layer 2 MAC address, okay, will know the layer 2 MAC address of this device as well within the same network. But once you know the MAC address of this and you go out of the network, then perhaps you have to communicate with another MAC address. But remember, as you are communicating with different MAC addresses, your logical address of the sender and the receiver is still the same. The layer 3 address, that is the network layer, is still the same. Okay? So what happens is, source has this MAC address, destination has this MAC address. Okay? So in order to communicate, you have to go through a section over here, okay, so that it is in the same network so that they can communicate. And this MAC address, the moment you go, this is your first hop, second hop, third hop. Every hop that you make, you will see the MAC address keeps changing. But your logical address will always be same. That means over here, your MAC address of the sender and the receiver is different. Again here, from sender to receiver, the MAC address will change. Again here, from sender to receiver, the MAC address will change. Again here, from sender to receiver, the MAC address will change. Again here, from sender to receiver, the MAC address will change. Again here, from sender to receiver, the MAC address will be changed. That is, your layer 2 data link layer address always changes. But your layer 3 network address, the IP address, is always the same. It comes from this IP address and it has to go to this IP address. Always the same. Okay. So at the first layer, okay, when you are sending, you see, from the sender to the router, you can see that your destination MAC address and your source MAC address is source MAC address, destination MAC address is this connection of the router. But if you look at your IP address, it's the same. This is your source and your destination. Now, when you go to the second hop, you can see in the second hop, you have got a new source, an IC, source MAC address, and a new destination MAC address. But look at your layer 3 network address is still the same. When you go to the next hop, you can see now you have got your source MAC address and destination MAC address. Again, it is changed. But look at your IP address, it is the same. Okay? So MAC address keeps on changing, but your IP address is always the same. Okay? In every section of the network. So this brings us to the end of this session. Okay, my dear students? Now, what you have to do is your actual task for today. The actual lab, which I call the first real lab, first real work, which you're going to do. And every lab, I told you, is like a exam where you do the lab and you show it to me. So today's lab is right over here, lab number 2.9.2. Okay, something we studied last week. Okay, you can follow the lecture on Moodle. I'm sure that you have studied, you have gone through it. I've told you every week we'll be covering one session with you guys and the other session with the 1 p.m. students. So you have to follow what is covered by for them, and they have to follow what is covered for you. Okay. So just go through the videos. Okay, those are just chapter videos, but the lab exercises that you all do will do the same. So this is your lab for today. You have to create a basic network consisting of a PC connecting to another PC. Okay, by using two switches. And you have to do this on packet tracer. And here's the topology, and here is the IP version 4 addressing that is given to you. Okay, so in the switch 1, you have to create a VLAN 1, and this will be the IP address. In the switch 2, here is your VLAN, and this is the IP address. In PCA and PCB, you have got two addresses. PCA is .10 and PCB is .11. Now a quick quiz. All of you pay attention. What is the network address of this network? Anyone? Please type it out if you know. Look at the addressing table. Yes, John Paul, very good. Dojian Yug, very good. 192.168.1.0, very good. How many devices I can add to this network? Yes, very good. John Yu and John Paul, 254. Now, how did you know this? By looking at the subnet mask. The moment you see this, you know that the only thing you can change is the last octet from 1 until 254. So why can't I use 255? Anyone? Yes, very good. 255 is reserved for broadcast. Well done, Cassandra. Okay, now I'm going to do this quickly on packet tracer. I installed a new packet tracer, the latest one, just yesterday. So let's play around with it. I'm sure most of you have got this packet tracer version 8. Okay, so if you go to sorry. I've got a big microphone here. Typing is difficult. Okay, this takes me to my packet tracer. So I'm going to replicate this network right in front of you, and then you're going to do the same for me. Okay, now I'm not going to do this every week. Perhaps some weeks I may do that since most of you are still new. So I'll be kind and I'll show you how to do it. Okay, so let's start with the PCs. This is my first PC, my second PC. So let's just label it properly. This would be my PCA, okay, and my PC B. Okay, And then we go to switches. Okay. So here are my switches. I select the 2960 series. Okay. Keep looking at the topology. Make sure that you follow the topology. Okay. So this is the task you're going to do today and show it to me. So this is S1, S2. Okay. So again, we call it display name S1. Sorry, S1. Here, display name. You can even type it there. S2. Okay, so there we have S1 and S2. Now, the wiring, okay, so we're using straight through all around. So from PCA to switch 1, you're connecting PCA to fast Ethernet 6 of switch 1. Please follow exactly this. So I connect fast Ethernet 0 of PCA to fast Ethernet 6. Okay, you can connect to any, but as the topology says, connect to 6. So we connect to 6. Okay. The other one, connect to fast Ethernet 18. So again, PCB, connect to fast Ethernet 18. Then from switch to switch, fast Ethernet 1, connect to fast Ethernet 1. So here we go. Connect fast Ethernet 1 to fast Ethernet 1 of the switch. So when you create a network, you see in the beginning, it will be amber. Okay, even your real devices, you will see amber light. And then it will convert into green. The moment you see green, that means the physical network has been set up. Okay, but you still cannot ping from here to here because you have not given the logical address. Okay, so here the MAC can communicate with this MAC. Okay, now this MAC can communicate with this MAC, but you have to set up an IP address to actually ping, which you have not set up yet. Okay, so that's our task. We're going to set up a IP address. So here we have PCA is 192.168.1.10 and PCB is 11. So let's just go and do that. Okay, desktop IP configuration. That is 192.168.1.10. Okay, automatic subnet mask is given 255.255.0. So the default gateway, there is no address. Why? There is no address for your default gateway. Can anyone tell me why I don't have to type a address for my default gateway? Anyone? Very good, John Yu. Because there's no router. Okay, the outgoing router's address would be your default gateway. Since you don't have that, you don't have to give that address. Okay, there's no router in this network. Okay, so PCA IP address given, done. PCB IP address 192.168.1.11 and automatic subnet mask. Okay. Here you can also give IP version 6 address. Okay. Now, if you observe, the address that we are giving is static. But if we want the router or perhaps an DHCP server to give an automatic address, then we select this option. For IP version 6 also, we can select this option. Okay, we're not doing that. Now, for our introduction to network, CCNA1, we always give static, okay, so that we understand the concepts and IP addressing and all that. So PCA IP address is given, PCB IP address is given. Now, what we have to do is we have to go to our switch 1 and create a VLAN 1 and give it this IP address. Okay, so let's do that. So I go to my switch 1, I go to my command line interface. Okay, in my command line interface, I'm going to type out my commands. Okay, there is my switch prompt. Okay, so I go to the privilege exec mode, enable. Now that I'm here, I go into configuration mode, conf T. Here, I'm in my configuration mode. Now, I want to access my VLAN 1. I say interface, VLAN 1. There. Now I'm in the interface mode. Now I'm going to give my IP address. IP address 192.168.1.1. Subnet mask 255.255.255.0. Okay. No shut. That's it. The state is up and the IP address is given. Okay, done. So I want to see whether this IP address has been given. Okay. Show running config. It shows me all the interfaces I have, and at the end, you can see after the 24 ports is shown, you can see your VLAN IP address 192.168.1.1. Okay, done. Now, I'm done with this. Now I go to my second switch. My second switch is VLAN 1, 192.168.1.2. So I go to the second switch. Again, I go to the command line interface. Okay. There we go. Enable conf T for my switch 2. So if I type here, show thing config. See the interface VLAN 1, there's no IP address. Can you see that? No IP address. Okay. So let's go and give an IP address. Okay. So configure terminal interface VLAN 1. IP address 192.168.1.2. Subnet mask 255.255.255.0. Okay. No shut. Okay. There we go. Exit. Exit. Another way, show IP interface brief. Okay, so when you say show IP interface brief, it shows you briefly, quickly, your IP interfaces. Okay, so two ways, show running configuration or show IP interface brief. I'm just showing you two different commands. So VLAN 1 IP address, and it is up and running. So we are basically done. Now, go to PCA, open your command prompt. Okay, so PCA, remember the IP address. The PCA, let's ping ourselves 192.168.1.10. This is PCA pinging itself. Reply, reply, reply. Okay, there we go. Success. Now let's ping PCB, which is 11. Okay, reply, reply, reply. There. Network is up and running. Now from PCA, let's ping our VLAN 1 in switch 1, which is 1. So the first time when you are doing this, okay, The first time will be request, then it's going to get reply, reply, reply. If you repeat, now you'll get 4 replies. Okay? Because the first time, the Mac is trying to find the other Mac, so it takes some time. Okay? So the first will be a echo request. Then the other will be echo reply, reply, reply. Now, let's go and find our, let's ping this section, okay, which is your switches VLAN 1, okay, which is 2. Again, the first one will be an echo request, and the other 3 will be a reply. There we go. Okay, now if I do the same thing, I get 4 replies. There, network is up and running. What about from PCB? So, sorry. From PCB, I'm going to ping PCA 192.168.1.10. There. Communication is perfect. Okay, no issues. What about if I want to ping from my switch 2? Okay, so from switch 2, ping to, let's say, I want to ping to my PCA. Okay, so ping 192.168.1.10. There, success rate 100%. What if I want to ping to my PCB? Success rate 80%, first time, second time 100%. Okay, why 80%? Because the first one will be a request. The first time when you are sending the ping, it's finding a device, so it's 80%. Second time it will be 100%. Now every time you ping, it will always be 100%. Okay, now your task, my dear students, is to do this and show it to me for today. That's your first lab, your actual first real lab. Last week, your first lab was creating a peer-to-peer network. Okay, child's play. But now you're going to professional domain. Okay, so I'm going to stop the recording now.